Hey there, this is Mr. Wilford, and I just wanted to go through and talk a little bit about Chapter 6, Section 9 with you here, Curve Fitting with Polynomial Models. We have been talking a lot about polynomials in this chapter, and one of the things that we've talked about here in the past, we've talked about different ways of finding the roots or the zeros of a polynomial. We've also talked a little bit about the different graphs of the polynomials as well. And how as we go up in the degree we kind of add another curve to the graph as we go through the polynomials. And we've talked about some of these that you can see here listed here: linear, quadratic, cubic, quartic, quintic, the degrees of those. What we're looking at in this section really is taking information, taking basically points or data, and we're trying to identify or fit which one of these polynomial functions our data would fit the best. And one way to do that is to use what we call the finite differences. And the finite differences can be used to help us find the degree of that polynomial. And we've done a little bit of this already with quadratics. Now we're actually just taking it a step further and dealing with polynomials. So here are a couple of examples. Basically what you do is you look at, well, first of all, the x values, if you notice, they're constantly going up at a constant rate. Here they're going up by 1s, here they're going up by 2s. So as long as they're constant, we're fine. Then what we want to do is actually take a look at the y values and take the differences. So here you can see they just pull the y values out here. And the first set of differences, so basically you can start at the end and subtract the previous. So 8 minus 2.4 is 5.6. 2.4 minus 0 is 2.4. 0 minus a negative 1.4. Two negatives make a positive 1.4, and so on. So you get this first set of differences. These are not relatively constant, so this would not be linear. So then what we do is go to the second set of differences. 5.6 minus 2.4 is 3.2. 2.6 minus 1.4 is 1. 1.4 minus 2.6 is negative 1.2, and so on. And this is the second set of differences in blue, and that's relatively not constant, so it's not quadratic. So then you keep going, and you do the next set of differences, and you find out that this is constant. So that means this would fit a cubic polynomial. That's what would best describe these data points. And they do the same thing here as well. You can see they go through the different set of differences, and it's not until they get to the fourth that this would be a constant, so we would have a quartic polynomial would best describe that table of values. Now, one thing to note is as you go through and you do some of the real world problems, you're going to notice that sometimes you're going to get relatively close. You might not be exact like these examples. These are set up for us pretty nice, as in this example here is going to show us. So here we have a table of years. So we're going up by 10 years each time, and we find the set of differences. And you can see here, right here, as we get to the third set of differences, these are relatively close numbers, closer, I guess, than what you would see here. So the easiest way to find what polynomial this would fit then would be to plug this into a graphing calculator and use the cubic regression feature on that. So basically you're going to plug in these values for x and y, and you're going to press the cubic regression, and it will give you this cubic function out. Now if you don't have a graphing calculator, sometimes you can find one online, and that's what I did here. And I have a link to this in our course. And you can see here what you actually do is plug in the x's and y values in here, and then you can pick one of the regression formats that you want and then plug that in, and it will give you the regression formula up here. If you have questions with this, please let me know. Thank you very much.